Hello everyone, I'm Sebastian Y and this is Managerial Economics. Over the next few videos we will cover the theory of individual behavior. First we'll talk about consumer choice theory, including utility functions and preferences, budgets, and the consumer equilibrium. We'll finish up by applying what we've learned to the principal agent problem. In this first video I'm going to cover utility and preferences. In the last set of videos we talked about demand functions, and how prices of goods, income, and other factors influence the quantity demanded. Demand functions arise from the choices that consumers make based on their preferences and their budgets. Understanding how these preferences and budgets work is important for a manager to be able to provide incentives for their customers. The math in these videos is going to take a bit of a step up from last time. What we're going to be doing is multivariate optimization. This means we're going to be doing a lot of partial derivatives and then some algebra to figure out what goes on. My advice is to just be careful, go slowly, and remember your derivative rules. Before we jump in, let's get a few basic definitions out of the way. Consumer choice refers to the process of a consumer selecting the amounts of each good that's available to them to consume. A bundle is a combination of goods that a consumer could potentially choose. Each bundle consists of an amount of each of the available goods. Consumer opportunities are the bundles that our consumer can afford to choose. Preferences determine which bundle they will select among those available bundles. Throughout these videos, we are going to assume that there are two goods, good X and good Y. Each bundle that's available to our consumer contains some X and some Y. So we will describe a bundle using an ordered pair X, Y, where the variable X is the amount of good X being consumed and the variable Y is the amount of good Y being consumed. As we go through the topic of preferences in this video, we are going to think about 4 different properties of preferences. Property number 1 is completeness. Completeness states that a consumer is able to fully express their preferences over bundles. Suppose we have 2 different bundles, Bundle A and Bundle B. Bundle A and B each have some amount of X and Y in them. Completeness states that one of the following statements must be true. A is preferred to B. 2, B is preferred to A, or 3, the consumer is indifferent between A and B. Our consumer needs to be able to say which of these is true for any 2 bundles. The curly greater than less than signs just mean prefers, and the tilde here just means they are indifferent. Basically, this says that a consumer is able to express their preferences across bundles. Mathematically, we use utility functions to help us do this. A utility function is denoted U of X and Y. This gives us a mathematical relationship between the quantity of X and Y and the overall level of satisfaction. We put in an amount of X, we put in an amount of Y, and then we get some number out. That's our utility. There is a direct relationship between utility and preference. If bundle A is preferred to bundle B, that is equivalent to saying the utility that the consumer gets from bundle A is greater than the utility they get from bundle B. If B is preferred to A, that means that the utility the consumer gets from bundle A is less than the utility they get from bundle B. And finally, if the consumer is indifferent between the 2 bundles, then that means the utility is exactly the same. This is all that utility does. Utility is ordinal, meaning if you get more utility from one bundle than the other, then you prefer that bundle to the other. Utility is not cardinal, meaning that if bundle A has twice as much utility as bundle B, that does not imply that the consumer likes it twice as much. It just means they prefer it to the other. All utility does is determine the order of preference of bundles. One of the most common utility functions that we see in econ is called the Cobb-Douglas function. Cobb-Douglas functions are of the form x to the a, y to the b, where a and b are just constants, they're just numbers. We will be working exclusively with Cobb-Douglas utility functions. The relative size of a and b tell us the relative importance of good x and good y to our consumer's level of satisfaction. We are going to use an example utility function for the rest of these videos. U of xy equals x to the 1/3, y to the 2/3. The fact that they add up to 1 here will make some of the math a little bit easier, but that definitely doesn't need to be the case. The next property of preferences is more is better. More is better states that if bundle A has at least as much of all goods as bundle B and more of some good than bundle B, then A is preferred to B. To illustrate this property, let's look at an example. On this graph, we have 3 bundles, bundle A, bundle B, and bundle C, each with different amounts of good X and good Y. First, let's compare bundle A and bundle B. We can see these two bundles have the same amount of X, but bundle B has more of good Y. More is better tells us that the consumer must prefer bundle B. Now comparing bundle A and bundle C. Bundle C has more X and more Y than A, so it also must be preferred to bundle A. Let's compare bundle B and bundle C. Bundle C has more X, but bundle B has more Y. More is better does not tell us which of these will be preferred, because we don't know how much X our consumer is willing to give up for Y yet. We'll need to know more about the consumer's preferences to be able to make this call. If we suppose that our consumer has our example utility function, which is U of xy equals x to the 1/3, y to the 2/3, we can then plug in the numbers to figure out the answer. For bundle B, we have U of 4 and 8, so we take 4 to the 1/3 times 8 to the 2/3. This is approximately 6.35. For bundle C, we take U of 6 and 6. That's going to give us 6 to the 1/3 times 6 to the 2/3, which is 6. Since the utility that the consumer gets from bundle B is bigger, then that tells us that our consumer prefers bundle B to bundle C. But note here that more is better did not tell us this. We had to plug it into the actual utility function. Before we get to the third property, we need to do a little bit of preliminary work and definitions. The first of these is the indifference curve. An indifference curve is a curve that connects a collection of bundles that give our consumer the exact same utility. That is, they are indifferent between all of those bundles. Let's sketch a graph with good X and good Y. Indifference curves generally have a shape that we call convex to the origin, meaning they bow inward towards the origin. If we look at a few points along our indifference curve, these points represent different bundles that give the consumer the exact same amount of utility. So if we label these up with bundle A, B, and C, our consumer is indifferent between A and B, indifferent between B and C, and also indifferent between A and C. If given the choice between these three bundles, they would be equally happy. A consumer has an infinite number of indifference curves. We can draw another indifference curve, something like this, and graph out some more points. Let's just call those D, E, and F. The consumer is indifferent between D, E, and F, but since this indifference curve is farther out from the origin, all the points on the red indifference curve are preferred to all of the points on the black indifference curve. I could also draw a lower indifference curve down here with some more points. Let's call them G, H, and I. Again, the consumer is indifferent between G, H, and I, but all of the other points we've drawn out are better than those because they are on higher indifference curves. When you draw indifference curves, they don't have to be artistically perfect, but they do need to follow the general properties of utility functions and indifference curves. One of the most common mistakes I see is drawing indifference curves that bend back, like I've drawn here. When quickly drawing them, it's very easy to make this mistake. The problem with an indifference curve that looks like this is that it violates the property of more is better. If we look at point F and see about how much of good y it has, we could keep going all the way over to this point right here. Let's call that point J. Point J has the exact same amount of good y as point F, but it has more x. By more is better, J must be preferred to F, but that could not be the case if they are on the same indifference curve. So you can see that we've just violated more is better by drawing the indifference curve this way. So I'm going to take my eraser and I'm going to get rid of those portions of the indifference curve that are bending back. The graph you see here are three different indifference curves for our example utility function x to the 1/3 times y to the 2/3. These three indifference curves correspond with a specific level of utility. All the bundles on the blue indifference curve give our consumer 4 utility. All of the points on that curve satisfy this equation. X to the 1/3 times y to the 2/3 equals 4. So if we took any of the points along that blue curve and plugged them in to this equation, it would come out as 4. Same thing for the red one. X to the 1/3 times y to the 2/3 equals 6. And for the green one, x to the 1/3 y to the 2/3 equals 8. Notice how as the utility gets higher, the indifference curves move outward from the origin. We could draw in 100 more of these if we wanted to, whether that's bundles that are even better out here, bundles that are worse down here, or somewhere in between. Like I said before, there are an infinite number of indifference curves, which each correspond to a different level of utility. Since the consumer is indifferent between any two bundles on the indifference curve, this implies they are willing to exchange some of good x in exchange for some of good y to maintain the same level of satisfaction, or vice versa. The rate at which a consumer is willing to trade x for y is called the marginal rate of substitution of x for y. The MRS at any given point along an indifference curve is also the absolute value of the slope of that indifference curve at that point. We'll return to the concept of the MRS in a few minutes. Our next definition is marginal utility. Marginal utility is the amount of utility gained from increasing the consumption of one particular good, in our case either x or y. As is going to be the case as we move forward through this course, when you hear the word marginal, you want to think derivative. We define the marginal utility of x as the partial derivative of the utility function with respect to the quantity of good x. Similarly, we define the marginal utility of y as the partial of the utility function with respect to the amount of good y. We can use these to get our definition of the marginal rate of substitution of x for y, which is the marginal utility of x divided by the marginal utility of y. This is going to give us the rate at which our consumer is willing to exchange some amount of x for another amount of y. When they gain a little bit of x, they're going to get some marginal utility. When they lose some y, they're going to lose some marginal utility. And so if we take the ratio of those, that's going to give us the rate at which they're willing to exchange. Let's calculate these for our example. Our utility function is u of xy equals x to the 1/3 y to the 2/3. The marginal utility of x, we take the partial derivative with respect to x. When we take the partial derivative, we treat y as a constant. So y to the 2/3 just comes along for the ride, and we can just focus on the derivative of the x portion of this. Don't be afraid when we see fractional derivatives. We continue to follow the power rule no matter what the exponent is. The power rule tells us that we multiply by the exponent and then we subtract 1 from the exponent. 1/3 minus 1 is going to be negative 2/3. And remember that we're taking the partial derivative, so we treat y to the 2/3 as a constant, so that just is going to come along for the ride, and we multiply by that. For the marginal utility of y, we do much the same thing. This time we treat x to the 1/3 as a constant, so that's just going to come along. We follow the power rule for y to the 2/3. The 2/3 comes down, and then we subtract 1 from our exponent. 2/3 minus 1 is negative 1/3, and then the x to the 1/3 comes along. I am writing these out to preserve the order of x and y, but you definitely don't need to do that. Remember that the order that we write them in does not matter for multiplication. I just like to keep them in a consistent format. Next, we're going to calculate the marginal rate of substitution. I have been consistently saying marginal rate of substitution of x for y, but you can go the other way. I'm going to always keep things x for y just to keep it straight, but if you wanted to do it the other way, you could. You just need to reverse absolutely everything we do for the next 3 videos. So I'm going to keep it this way. We're going to take the marginal utility of x and divide that by the marginal utility of y. This is where it's helpful to remember our rules for exponents. If we have a negative exponent, that means we can move that part of the expression to the other side of the fraction and flip the negative sign. This means we can take our x to the negative 2/3, bring that down to the bottom of the fraction and get rid of the negative sign. And we can also take our y to the negative 1/3 and take that up to the top and also remove the negative. What we're going to get is 1/3 y to the 2/3. That stuff has just stayed the same. Now the y to the negative 1/3 has come up to the top, but just becomes a y to the 1/3. Since we flip the sign, the negative becomes a positive. On the bottom, we have the 2/3 still, the x to the 1/3 from before, but now the x to the 2/3 has dropped down to the bottom and we've flipped the sign, so that becomes a positive 2/3. We're almost done cleaning this thing up. First thing we'll do is resolve the 1/3 and 2/3. The thirds are just going to cancel, and so all we're left with is a 2 on the bottom. This makes sense because 1/3 is half of 2/3. So we're going to get a 2 down here. Next, we're going to combine the like terms, so y to the 2/3 times y to the 1/3. When we have two terms multiplied with the same base, we add the exponents. So we have y to the 2/3 plus 1/3, that adds up to 1, so we just get y to the 1 up at the top. We can just leave that off. And on the bottom, same thing happens. X to the 1/3 times x to the 2/3 is just going to be x. So you can see this thing started out a little bit intimidating, but if we just follow all the rules to simplify it down, it comes out to a pretty nice, clean expression. This is one of the big advantages to working with the Cobb-Douglas function, is that it always comes out pretty nicely. This brings us to our third property of preferences, diminishing marginal rate of substitution. This tells us that the more of good x we have, the lower the marginal rate of substitution. This means that the more of good x we have, the less willing we are to give up units of y for it. Think about a situation where the two goods we have are peanut butter and jelly. If you only have a little bit of jelly but lots of peanut butter, you're not going to be very willing to give up jelly to get more peanut butter. You already have a lot of peanut butter. But if you were in a situation where you had very little peanut butter but lots of jelly, then you'd be happy to trade some of that jelly for peanut butter. We can see this in action in our example marginal rate of substitution, that since x is in the denominator, the more x we have, the lower the marginal rate of substitution. Since the marginal rate of substitution is also the absolute value of the slope of an indifference curve at any given point, this is what gives indifference curves that characteristic convex to the origin shape. If we sketch one out, remember that they look something like this. As x gets bigger and we move this way on the indifference curve, that indifference curve is flattening out as the MRS is getting smaller. The fourth and final property we are going to talk about is transitivity. Transitivity states that if we have three bundles, A, B, and C, if A is preferred to B and B is preferred to C, then it must be true that A is also preferred to C. Similarly, if the consumer is indifferent between A and B, and also indifferent between B and C, then it must also be that they are indifferent between A and C. For example, suppose a consumer is offered a choice between a Coke, Pepsi, and Mountain Dew. If the consumer prefers Coke to Pepsi and Pepsi to Mountain Dew, then they must also prefer Coke to Mountain Dew. This property also implies that it's impossible for indifference curves to cross. If we sketch another graph of an indifference curve, this means all the bundles on this indifference curve are preferred to all the bundles on this side, and all the bundles on this side are preferred to all the bundles on the indifference curve and also the ones in the blue area. Now that we've covered the basics of preferences, in the next video we're going to move on to budgets.